Good evening, everybody. My name is Salvatore Anderson, and I'm a proud member of the Drexel team based here in Philadelphia, AKA Team Gritty. Our project advisor is Professor Peter Clellens, and we have 4 students working on this project, all engineers. I myself, a computer engineer, am working on the financial analysis. August Pendergast is working on conceptual design. Cassie Pezza is working on distribution impact, and the lead for the development plan is Kieran Van Sant. So I think we all have a relatively solid background on PNNL by now, but it is a DOE laboratory with 350 acres of campus. Its #1 goal in a PV system is seeking resilience to combat outages that occur on campus from their utility services. These outages create problems for ongoing research. And you can see here on the right of the slide, we have the requested ride-through durations and peak loads that PNNL gave us. And these were paramount in deciding the conceptual design going forward. This is the competition area. You can see the red border outline there is the limits of where we can install our equipment. You can also see that there is land that's preserved. And there's also land that's planned on being used for further developments of the campus and the installation of new buildings.
The secondary competition area in the north is exclusively ground mounted system and surrounded 2 important buildings that we wanted to develop. Shown as the orange box, the battery was placed next to building 1 with the arrays and associated equipment installed near the
August, you're a little quiet. I don't know if you can speak into the microphone just a little bit more.
Is this better?
Go ahead and I'll let you know if it's too quiet.
Okay,
Thanks.
sorry. 2 buildings in this area, building 318 and building 331, require at least 224 kilowatts for 4 hours, and our system can provide this daily. Otherwise, offsets more than 6% of the building's regular energy. In the south, our system placement is more nuanced because you can consider the installation of carports and roof mounts as well. The buildings demanding the load are to the north of this area, with rooftops and parking lots between the buildings and the final system location. While the most obvious placement for our solar array was the roof of VMSL, the building closest to the other 2 buildings. Exclusively installing ground mounts had a 1.24% installation cost saving. On top of this, loss of power production due to shading on the roof of VMSL and the need to expand to another area of campus to make sure our system is recharging the battery fast enough, it was decided to place the panels in the open field to the south of the core campus. A huge benefit to this location is how easily it integrates into PNNL's campus. The city of Richland is south of the campus, and the major roads running north and south between the city of Richland and the core campus pass the arrays, being a visual reminder of PNNL's goal for carbon neutral power production and an indication of the vital research that happens on campus. Shown here is the south system. Though both systems have the same array orientation and similar layouts, you can see in the image on the left the trees that surround the arrays. To the south of that, there's a cluster that shows where the shaded recreational area is, and the major roads running past the arrays between the city and campus showcases the project. To maximize energy production, the mounts are tilted at 46 degrees and face due south. Across campus, the tilt and orientation factor is 99%, it's the highest possible. To allow for easy maintenance, these panels are mounted too high, and the top of the final installation with concrete mounts won't be taller than 12 feet. Using PNNL's security detail criteria, the panels were spaced from the major roads 80 feet, providing a soft barrier while still giving ample space to install fencing if needed. The rows of arrays are spread out 120 feet, there's minimal self-shading. In the north, there are no trees or buildings shading the panels, and all arrays have 100% solar access. In the south, there are some trees to the west and south, but all panels achieve between 99 and 100% solar access, resulting in a total solar resource fraction of between 98 and 99%. So aside from the great solar resource usage of our system, the equipment we utilize makes our proposal the best. With panels more than 18% efficient and at 41 cents per watt, there's no competition for the effectivity of our solar arrays. Connected to commercial DC optimizers and high power inverters, our system has minimal power loss between the arrays and the batteries. Total power connected to each inverter is oversized by 21.8%. This is slightly higher than the industry recommendation, but the system experiences no energy clipping throughout the year. While our system operates, the battery will remain between 20 and 80% charged to lengthen its lifespan. When fully charged, the system will be utilized to offset the building's load, saving PNNL money and relieving the grid of some of their demand. Providing backup power for the system was our primary focus, and the data PNNL provided indicated there were more frequent outages for the buildings in the north than in the south. Accordingly, this system has a faster recharge time. To summarize the resilience of the system, in months of high production, each system can be available within a day of full discharge. And when production is lower, the system will recharge to provide the critical load within.
When designing the system, we focused on mitigating any potential distribution system impacts, both behind the meter and beyond the meter. In terms of behind the meter, the system equipment was arranged to comply with each component's electrical requirements. Wiring the panels in series to the DC optimizers was the best option for our system because there's no risk of overpowering the DC optimizers, as shown in the graph on the table on the top. The inverters are arranged such a way to limit the DC wiring between the optimizers and the inverters. As shown in the slide, the maximum output of each panel series layout remains below the maximum input allowed for the DC optimizers and the inverters. Additionally, the connecting wire will be gauged accordingly to comply with the NEC standard, eliminating voltage drop below 5% overall and 3% in each branch. In addition to behind the meter distribution impact, the team also considered potential impacts that the PV and battery storage system would have on the electric grid's distribution system. Due to limitations in Richland Energy Services, the system was designed such that no power was exported to the grid. If this decision were to be reevaluated, the placement of the panels would need to be modified based on the heat map shown in this slide. The campus has the large PV capacity in the area where the north system is located, the bright yellow in the top right corner. And then in the south area where our EMFL building is located, PV capacity is slightly limited, so we would most likely need to distribute the panels so they're not all in the same lot using the same wiring to go onto the distribution system. If we go to the next slide, there are several other strategies to mitigate that though. So you can do alternate routing where you're not connected to the same transformer or same wiring. You can reinforce the grid so that way you're either upgrading the gauge of the wire or you're upgrading your transformers so they can host more PV. There's also reactive power and active power curtailment, so that way you're limiting how much you're actually exporting. These options aren't the best because they limit basically they have negative impacts on your loss. And then you can also utilize energy storage to limit how much you're exporting to the grid. In our case, that would be the best route because we are already designing a system with storage for the resiliency of the system.
So when it comes to the individual components of the system, we were able to add them all together by taking the certain components that we knew specifically how much they would cost, such as the module, the battery, inverters, a number of the BLS components, and then compounding that with general overviews that we saw for other photovoltaic systems in the energy cost storage benchmark. And we took the components for a 1 megawatt system, which is similar in size to our total system. And then we extrapolated those components to the 133 megawatt system that we're implementing. And then we took that, got the cost per watt in DC and added that up. Our overall cost per watt was around $2.08. And that is relatively high, but that does include the battery. And it is important to note that our system was designed specifically to combat outages as opposed to trying to offset any of the utility costs because the utility costs are so low. So in terms of the individual PPAs, it's worth to note that these individual PPAs are calculated as each individual system is looked at individually. not as a subsection of the total. So for the north system, we have a 12.5-cent PPA for the PV system alone, and a 14-cent PPA for the PV system and battery storage. For the south, that was a 10-cent PPA for the PV system, a 12-cent PPA for the PV and battery storage system. And for the system total, we had a pretty competitive 9-cent PPA for the PV system. And that increased to a 12-cent PPA for the PV and battery storage system. We were aiming to have a basis of an NPV of 0 and an IRR of 7.5, but we'll see that those numbers increased a little bit. For the overall costs and the bottom line, the first year costs, to give you a general overview, these were calculated with a 3% utility escalation rate and a 2.5-cent PPA escalation rate with a panel degradation rate of 2%. Overall, the system costs around $33,000 with a 20-year model, assuming that we go with the PPA. That is for the first year, and that cost will slowly decrease as the escalation rate of the PPA is lower than that of the utility costs. In the end, over 20 years, our total costs are running around $750,000. These are the net costs when you include the lessened cost of the utility offset and as well as the PPA.
So the construction timeline of the project is estimated to be completed over the course of 8 months. This process has 3 primary stages of development. The first is the final planning stage. So site surveys will occur to inspect the locations where the panels are planned to be installed. Any unexpected conditions will be reviewed to determine how the design may need to be altered. And during this, discussions will be conducted with district decision makers to finalize the project and hear of any of their input and concerns. Concurrently to the site surveys, there are necessary permits for the city of Richland and the larger Benton County in order to ensure our construction process and solar design complies with necessary zoning and codes. So the next stage of the process is procurement installation. The construction of the battery buildings and concrete mounting structures will precede the installation of the panels in the battery system. Due to supply issues that have been prevalent in the last couple of years since the start of the pandemic, more time has been allocated to be flexible with shipment delays. And then following this stage will be the process of post-installation testing and interconnection with campus buildings. Due to the positioning in the south lots, some underground wiring may be needed to connect panels with the battery buildings and campus loads. Next slide, please. So the municipal and county zoning maps for Richland and Benton County are shown here. The greatest restriction is from Benton County zoning on the south campus lots, which are also within the Richland city limits. They allow for minor solar generation facilities, but do not give a power limit for any installations. In the permitting process, securing county approval on the size of the generation will be needed. And in regards to North Campus installation, since it is outside the city limits, Benton County zoning will allow for major solar generation facilities, since that area is a light industrial classification. Next slide, please. Overall, the project provides PNNL with a robust ability to respond to outage events. The system will be able to handle multiple minor outages per day and recharge from 20 to 80% over the course of 1 to 3 days. The PV and battery system can be paired with on-site equipment like PLCs to provide power to the most critical loads in each campus building. And the panel, inverter, and battery combination has been chosen to provide a high level of efficiency, maximize power output of each string, and reduce overall costs. Next slide, please. These are our primary resources that our team used to develop and model our design. Of particular importance were System Advisor Model, Aurora Solar, and Energy Toolbase. Next slide, please. And then finally, we'd just like to thank our advisor, Professor Cullen, for his help, as well as the Solar District Cup organizers, and like to thank you all for your time today.